Thank you very much. 私はデンボルスティンです。日本語が少ししかできませんから、I hope you'll forgive me. The rest of this talk will be in English. Okay, I want to tell you just a little bit about my background. I joined Google in 2005 to work on the Android project, and I've been working on the Dalvik virtual machine almost the entire time. And in my previous history, I've worked on a few other virtual machines. So it's very exciting for me to be able to continue my personal work in this area. Although I did start this project, the virtual machine project, the Dalvik virtual machine would not be where it is today without the help of many other coworkers. So I have a huge debt to those people, so I have to say thank you. If you're curious about the name, the town of Dalvik, Iceland is in the northern central portion of the country. And if you're interested in going to visit the Arctic Circle, that's where you catch the ferry. Okay, if you're familiar with Android at all, you might have seen this diagram before. You can see that Android is a platform that encompasses the entire stack for a cell phone, or for a mobile device in general, from the low-level drivers at the one end, up through native libraries, through to an application framework, and also including several applications. And today, I'm just talking about this one little area, just the virtual machine. So what is the Dalvik virtual machine? What's the point of it? There are lots of virtual machines out there already. However, the constraints of the Android platform were such that there wasn't anything suitable to use for the project. And you can see here there's three of the things that we have to worry about. By desktop standards, we don't expect to run on a fast processor. We don't expect to have very much RAM. And the operating system isn't going to have swap space, so no hard drive. And in addition, of course, it has to be powered by a battery. And the battery issue is something that just keeps coming back as a design issue. So now that you know a little bit about our constraints, I'm going to tell you how we address some of them. In particular, I said we do want to run on low-memory devices by desktop standards. And here's just a few statistics about the low end of the system that we expect to run on. So in particular, the Android platform assumes that the processes are the units of trust and isolation. Therefore, anytime you have a separate application, that application has to run in a separate virtual machine in a separate process. And with other system services running, by the time the system is up and running, you don't have a lot of space left for applications. And that was a key problem that we try to solve with how we arrange the memory. In addition, of course, as a modern platform, we're trying to provide a rich set of libraries to developers, and that comes at a cost of memory. Okay, so this is just a very high-level view of what a Dex file looks like. And the Dex file, that stands for Dalvik Executable, is the file format that we run in the Dalvik virtual machine. You can see that after the header, there are 5 sections. Each one of these sections is a constant pool, and each of these constant pools holds a specific type of data. So you can see that at the top, there's the string IDs section, which holds literally references to strings. You can see the little examples off to the side. Type IDs are things that are like types in the language. You can, again, see examples. Protos, those are like method prototypes, so arguments and return values. Fields and methods, those are, again, the name and type associated with a field or a method. And after that, there is a list of classes. Those are the classes that are defined in that file, and then associated data that goes with all of that. And the deal is that each of those sections will point at data in the other sections. And this is not a complete diagram, but it gives you the flavor of the references. So this is just a simplified illustration of how a .jar file will get converted into a .dex file. And you can see that in the jar file, there are separate classes, and each class has its own constant pool and its own data. And using the tool that we call dx, that jar file, that set of classes, gets converted into a single dex file where each of the bits in the individual constant pools are split out by type, and the data gets mingled between all the classes. Okay, here's just a quick little piece of code. I'm not going to walk through it, but there's just an interface, an implementer of that interface, and then a user of that implementation. And we're going to see how that turns into both a set of class files and into a dex file. So here's that same piece of code represented, or the constant pool for that piece of code represented. So you can see that each class has again, it's a separate entity. And you can see that there's a lot of duplication between the different classes. So for example, in particular, the things that I'm pointing at here are the method signatures. So each one of these has a reference to the same method signature. And you can see that within the method signature, there's a lot of duplication of the names of the classes used. And additionally, you can see that there are these literal identifiers that identify different pieces of the class, of the classes. Here's the same set of classes represented in a dex file. What you can see here is that there's a lot less duplication. So for example, if you look at the bottom right, you can see the references to the class string and the class object. And those are the only references in the entire file. So in the actual file, again, the different pieces are separately collated, but I drew this diagram just so you could see how the references really point at each other. So using this shared constant pool, what we're doing is we're saving memory by avoiding the repetition, and by using the per type constant pools, we can remove redundancy. And because we're avoiding labeling the various pieces, we can save the memory that would otherwise be used to represent those labels. And here's just a few summary statistics. In each of these sections, the top number is a number of bytes of the uncompressed .class files for, at the top, the common system libraries, that's the shared libraries, and the web browser app in the middle, and just the alarm clock application. And these are actual numbers that I measured about a month ago, so things may have changed since then, but probably not by much. The middle number in each section is when those classes are represented as a jar file, and the bottom number is when it's represented as a dex file. And the interesting thing here is that the jar file is compressed, whereas the dex file is uncompressed. So if we went and compressed the dex file, we would actually save a significant portion. However, it's important to the way we run the platform that we be able to use a dex file in its uncompressed form. And I'll talk about that in a little bit. So on any modern platform, you can think of there as being 4 different kinds of memory. And those are 2 distinctions, 2 sets of a pair of distinctions. There's clean versus dirty, and there's shared versus private. The idea of clean memory is it is memory that your system, the low-level system, could drop from RAM at any time because it could recreate it, either because it's backed by a file so it can reload the file, or simply say it might be a page full of zeros, and the kernel knows that if it needs to make a page full of zeros, it can always just create one on the fly. Whereas dirty memory is memory that has been explicitly allocated by an application, and the kernel has no choice but to leave it in RAM because it has no way of recreating it. There's also shared versus private memory. And this is a fairly simple distinction. Private memory is memory that is only used by one process or by one application. And shared memory is memory that is used where the same memory is used across multiple applications. And the advantage of having shared memory, especially if it's dirty, is that the cost of that memory is amortized across all of the processes that are sharing it. So on Android, here's how those four kinds of memory end up getting used. So there's clean memory, and that's used by the common Dex files. And it's also used by the application-specific Dex files. So the common Dex files are going to be shared clean, and the application-specific Dex files are going to be private clean. And again, this is why it's important that the Dex files be usable uncompressed, because on disk or on flash memory, they can sit there uncompressed, and the kernel can page them in at any time. And if it needs to drop them from RAM, it can, and it can always just get them right back in from RAM. And on the other hand, the private dirty memory, again, it's what's left in memory at all times until the application explicitly drops it. And in the case of Android, we have, for every Dex file, there is some amount of live data that's associated with it that has to be allocated at runtime. And that's dirty memory. And the heap, the object heap of each application is similarly going to be private memory. And the big question that we tried to solve is how to make memory be, instead of private dirty, again, make it shared dirty so that we could reduce the overall system cost. And our answer for that is this thing that we call the Zygote. The Zygote is a special virtual machine process that starts up early on in the life of the system. So soon after boot, the Zygote starts. And it preloads and pre-initializes as many of the system classes as we believe will be used across many applications. And so the Zygote creates it creates the live Dex structures, it creates the heap, and then it sits and waits on a socket and waits to listen for commands. And when it gets a command, it will do a fork, a standard Unix fork, and then that new process comes into existence and gets to share that Zygote heap and those Zygote Dex structures. This is just a simple illustration of what's going on. You can see that there's the Zygote process, and then each of these applications, instead of having its own copy of these library Dex files, this heap of objects that was created by the library, instead of having it separately, they're all just pointed at, or each of the applications points back at that Zygote memory. And so that answers the question, how do we get shared dirty memory in the system? So in conclusion for this part, our goal is to get as much clean memory as possible. And that's why we work so hard to make the Dex file usable uncompressed. But if we can't make memory clean, at least we can get it to be shared dirty. And so that way we minimize the amount of private dirty memory. And on that note, we have to do some special consideration with respect to garbage collection. Dalvik has a fairly simple stop the world, mark and sweep garbage collector. And for this kind of garbage collector, there are two different strategies that you might use to represent the extra information that you need while garbage collecting. And you can see on the left, you can embed that garbage collection information, the mark bits. You can embed it with each object. Or on the right, you can see you can have this separate area of memory where the mark bits live. And if you're just considering a single process, the debate can really go either way. You can consider the cache effects of having your mark bits be conveniently located, so when you're doing a garbage collection, those mark bits are sitting next to the memory that is going to be accessed soon thereafter. Or on the other hand, if you have the separate mark area, then when you're not garbage collecting, you have much better cache locality for the main operation of the program. However, in terms of how Android has to function as an entire system, you have to take into consideration that there are separate processes. There's not just one virtual machine on the system. And each process has a separate heap. Each heap has to be separately garbage collected. And the garbage collection should not cause two applications to interfere with each other. And that really meant that for Android, there was only one answer. And that is to keep the garbage collection information as separate from the main heap. And this is especially true for the Zygote, because if we were to have the mark bits interspersed with the heap in the Zygote process, in the Zygote heap, when each application did a garbage collection, it would immediately force those pages to be unshared as each garbage collection twiddled with those bits individually. And there's one additional advantage that we get, and that's because most of the time a program isn't garbage collecting, you don't actually have to have those mark bits allocated. So, when a GC gets invoked, the system will simply allocate the mark bits for that garbage collection right then and there. It'll use it, it'll do the garbage collection, and then it can free that memory back up. Okay, so that covers a little bit about what we do about the memory on the system. And now let's look at what we do about CPU performance. So this is what a typical Android device may look like at the low end. So again, by desktop standards, a fairly slow CPU and a fairly low bus speed, almost no cache by desktop standards. And again, I just want to emphasize, not much RAM is available after the system gets fully booted. So before I tell you what we are doing, I'm going to tell you one of the things that we're not doing. So we're not doing just-in-time compilation. And the simple summary of that is that you can always imagine a program that could use just a little more CPU. However, we went through great pains to provide native code to do a lot of the heavy lifting on the system, such that for the vast majority of applications, and this is even including things like games and 3D, so for the vast majority of applications, you don't need to have native code, and you don't need to have your own native code, and you don't need to have your own code run at native speed. So now that I've told you what we don't do, here's what we do. At the time an application gets installed, we do a lot of work. And that work is meant to to be done such that so that when it comes time to run the application, you don't actually have to redo that effort, or you don't have to do that effort every time. So one of the things that we do is verify the contents of a Dex file. And what this means is we parse all of those sections of the Dex file, and we make sure that everything that's pointing back and forth is pointing to something that makes sense within the context. And we do a code verification so that we know that code that runs is incapable of violating the constraints of the virtual platform. We also do a number of optimizations on the code. So for big endian machines, we can byte swap. It's unnecessary on our expected targets, but we could do that if we had to. We also do a number of static linking steps. And what we do there is, for example, take a symbolic method reference, so where you have like the class name and the method name and the arguments, and instead of representing those in that sort of full form, we link it to, say, a particular index into a vtable, so that when it comes time to execute an invocation, we can simply do an indexed lookup instead of having to, say, look up a method by name and match the parameter types. So perhaps the most radical thing that we do in the Dex format is redo the instruction set entirely. And instead of having a stack machine, and this is what the original .class files have, or rather that they represent, we use an infinite register machine where within each method there's only registers. Where with when methods call each other, there's still a stack, but within each method it's all just register references. And what this means is that we can have instructions that where each instruction has more semantic density. And what the semantic density means that we can dispatch fewer instructions. And for an interpreter, one of the biggest components that contributes to poor performance is the number of instruction dispatches that you do. So by avoiding instruction dispatch, we increase the overall performance of the interpreter. In the DX tool, the tool that takes .class files and turns them into Dex files, we do some amount of optimization when we translate from a stack machine to a register machine, and here are the results. Again, I measured this about a month ago on our overall system. We have about 30% fewer instructions than the originals, and we have 35% fewer code units. And I'll tell you what that is in just a second. But we have 35% more bytes in the instruction stream. And the distinction here is that in a .class file, the code unit is a single byte. And that's because many instructions are themselves just a single byte. So if you had more than that, you would be wasting a lot of space. However, because each Dalvik instruction tends to have more information in it, we picked 16 bits, 2 bytes, to be the code unit. So when we are interpreting Dalvik, we end up reading these 16 bits at a time. And that means that we get to consume the instructions on a byte-by-byte basis twice as fast. OK, now I'm going to walk through just a little example here. And we're going to see what this looks like both as an original .class bytecode and as Dalvik bytecode. This is just a simple function. It sums the contents of an array. You can see that. This is what it looks like as a .class file. I've marked the main loop in red so you can see it a little easier. And I've annotated it with reads and writes to local variables or registers and the stack. And you can see the summary statistics there. So that's for each iteration of the loop. There's 25 bytes worth of instructions. There's 14 instruction dispatches. And if you add it up, there are 45 reads, and that includes reads of the instruction stream as well as reads of stacks and locals. Similarly, the 16 writes are writes back to the stack or writes to local variables. On the other hand, this is what it looks like as a Dex file. So you can see that it's actually much more compact. And this turns out, in this case, although overall the number of bytes in Dex files tends to go up, in this case we actually see that this inner loop has fewer bytes. And that means fewer reads, better cache behavior, many fewer instruction dispatches, and also many fewer reads and writes. And if we look back at let's see if I can do that. Look back here, you could, with a clever interpreter, you could get rid of about, say, 6 or so of those reads and 6 or so of those writes. But even so, it's still not going to, it still doesn't win compared to our Dex version. So this is just another example. And this is an example of just representing an array of data, of simple data. Because sometimes in your code, you just need to have an array. And unfortunately, in a .class file, code that looks like this turns into code that looks like this. And there's a lot of effort that has to be done to initialize each of those elements. So in this case, it's, I think, 44 bytes of instructions for that 7-element array, and another 35 bytes in a constant pool, and so it's almost 80 bytes total. And if we wanted to add another element to that array, it's 11 bytes of code in constant and 4 additional instruction dispatches. And all of this activity has to happen on the stack and in memory, and so that it can be fairly slow and again eat up a lot of space in your code. So a lot of people are aware of this problem, and there's a standard workaround, and this is what it looks like. So in this case, I've represented the same data as a string, and then I have a little for loop that decodes that string into the array. This still has some advantages, where in that it's a more compact representation. It doesn't bloat your code quite so much, but it still has some disadvantages. For one thing, the UTF-8 representation of that string is still a little bit bloated, because each pair of bytes there will turn into 3 bytes in the class file. So that's what, a 50% increase in size typically. And in addition, in order to expand it, you have to run that loop, and that loop is going to be a lot of code, or a lot of execution time, relatively speaking. So instead, this is what we have in a .dex file. You can see that on the 3rd instruction, that's fill array data, that single instruction causes the entire array to get filled in, and the data for that is down at the bottom where it says array data. And you can see that there are 7 elements in that array data, and the representation is exact. So there's no penalty for decoding. In fact, there's no decoding that you have to do. It's simply the data. And so in this case, it's just 46 bytes total to do this. And again, if you wanted to add another element to this int array, it would just be another 4 bytes. So for example, I'm adding, 6 elements here. So I'm adding simply 36 bytes to the representation. Just in case you're curious, there's that no-op there. We do that so that when the array data instruction is sitting in the Dex file. It's aligned on an int boundary, so that way we can have a little bit more efficiency in the interpreter. And now I'm just going to talk a little bit about what we do for the interpreter. So this is just a very simple toy example interpreter, just as kind of a baseline. This is a fairly simple system. We were just in a loop looking at each character in this string and dispatching to a little piece of code to execute for each one of those characters. Instead of having characters there, you can imagine those being more complicated opcodes that take arguments and so on. But that's beside the point for this example. So there are a couple inefficiencies here. You can see that there's an outer loop. And so in order to implement that outer loop, there has to be a branch back from the bottom to the top. And then for that switch statement, there has to be a branch from the beginning of that switch statement into whichever case you go to. At the end of each case, there has to be a branch back to the bottom of that for loop. That's a lot of branching. And thankfully, there's a standard extension to the GNU C compiler, and that's known as computed goto. So this is one case where goto isn't evil. What GCC lets you do is take the address of labels and use those as elements in an array, and then you can look up those elements and then effectively branch to them directly. So in this case, you can see that at the end of each opcode, we simply directly dispatch to the next one. And so that avoids a few of those jumps that we saw in the first example. However, even the best compiler still doesn't quite do as well as a human can in real examples. It breaks down a little bit for this toy example, but I just wanted to show you what this same strategy looks like as ARM assembly. And what you can see here is that each instruction dispatch requires 2 reads of memory. The first read is to read the instruction itself to get that opcode. And then the second read is to read from that opcode table to find the address to branch to. And the deal is that we can do better. And we can only do better in assembly at this point, because what we can do is, instead of having each opcode take however many instructions that opcode takes, so some instructions don't take much code and some instructions take a little bit more, we can take a typical instruction size such that we get at least the most of the instructions, and that turns out to be, for us, 64 bytes. And what we do is make sure that each opcode is aligned on a 64-byte boundary, so that way, instead of having to do a table lookup to find the address of an opcode, we can just have the address of that first opcode, and then just do a simple multiply and add to get to that to do that dispatch. And so we save 1 read per dispatch. And again, because dispatch time dominates what happens in an interpreter, anything that you can do to speed up that dispatch is going to give you a huge payoff in terms of interpreter performance. Okay, now that you know a little bit more about the design of the virtual machine, I just want to take a couple minutes to tell you how you might optimize your code a little bit for the Dalvik virtual machine. And actually, this advice really applies to mobile devices in general. So I tend to think of the optimization problem in terms of timescale. There's at one end, there's the human interaction scale, and that's if you're a fast typist, you can type about, say, 10 characters per second. If you're using a mouse or a pointer or your finger, about, say, 15 or 30, say, readings per second is about all you really need. And bumping up a notch from there, there's the human perception scale. That's, say, for video, 25 to 30 frames per second is plenty. And for continuous audio, you need to be synchronized within about 100 milliseconds. If tighter than that, a human won't notice. A little looser than that, and you might start to see, say, like voices not being in sync. And then at the other end of the scale, there's computer scale, and computer scale is just when your code is running as much and as fast as possible. And the optimization problem, from my perspective, is simply trying to avoid computer scale. And the deal is that if what you're doing requires the computer to be constantly active, then your battery life is at stake. And so if you can simply limit your interactions, or limit your code to only run at one of those human scales, you're doing the battery a favor. And so with that, my first piece of advice is simply for your app to get plenty of rest. So an application is best behaved when it's simply sleeping and waiting for either user input or, say, for network input or something along those lines. And when that input comes in, the application responds. So like if you type, you show that key, and then it goes back to sleep to wait for that next event. But of course, sometimes you do have to have a loop, and those loops sometimes do have to operate at computer scale. And when you do, my advice is to loop wisely. So here I just have 7 typical examples of a for loop. And I've arranged them from about the most efficient to about the least efficient. Of these, the first 3 are almost indistinguishable in performance. And because the first one is a little unusual, it's a little unnatural for many cases. So I would just say, if you can make your loops look like one of these, then you're doing pretty well. On the other hand, if you have to operate at computer scale, that means doing a lot of loops, then please avoid using the heavyweight iterators, because each iteration, or each time you run that loop, you're allocating a new iterator, and allocation costs, especially on a device, again, that is running off of battery, because each allocation means you're using a little bit of the battery. And so my final piece of advice is simply avoid allocation. And it's a bit of a bind, because obviously you have to, in order to get anything done, you're going to have to allocate at some point. But just be aware, if you have a bunch of short-lived objects, they're going to have to get garbage collected. And that garbage collection takes energy, takes battery. And if you have a long-lived object, well, that's taking up memory that your user wants to have to do something else. So there's that tension, but really the resolution is that if you can allocate something and that allocation helps move you from computer scale to one of the human scales, then that's a good allocation, and that's a worthwhile allocation. And that's pretty much all I have for you today. Just wanted to, again, say that the Dalvik virtual machine it's a result of these pressures for operating on a constrained mobile device, and we've done a lot to help make it operate as well as possible in this environment. But with just a little bit of work on your part, you can have really good apps that run really well on mobile devices. And I hope this overview has helped you. So thank you.